Hello and welcome to Math 103 for Go Community College. We are halfway through chapter 4 right now. We're in the polynomials chapter, to remind you, and we're going to discuss multiplication of polynomials. As a refresher from the last couple things we've talked about, we previously discussed binomials, how to interact them together, clumping like terms, things along those lines. If you have any questions about that, shoot me an email, comment down below, or go back to your notes, right? Today we're, of course, as I said, going to be discussing multiplication polynomials and other things. So let's begin. When discussing multiplication polynomials, this is kind of your bread and butter of algebra, essentially, especially in this class. This stuff will eventually be linked in with the factor we talked about prior to let us do big math equations that are more akin to stuff we'd seen in the real world. And yeah, a lot of this stuff's going to seem kind of repetitive, kind of straightforward, but the practice makes perfect. So I say in all the videos every single time. When I get to a question, if you would like to, if you're watching this via YouTube, pause the video when I get to a question, try to solve it, push play again once you finish it to make sure that your work lines up with mine. That's the best way, in my opinion, to go about dealing with these situations. We've talked about this already, I believe, in class, but as a refresher, we can talk about monomials and polynomials, how to work them together. And of course, if you have a monomial multiplied by a polynomial, in this case a trinomial, 1, 2, 3 terms, it's a distribution conversation you're having here. The 3a needs to be distributed throughout. Of course, noteworthy here, this 3a has a negative sign in front of it, so you need to distribute the entire clump of negative 3a throughout. Once distributed as such, you then deal with each individual term connection, right? The negative 3a times the a squared, well, as I've said before, you can sort of argue the treatment of this would be to do the math of the numbers, then I used to say bring the letters along. In this case, do the math of the letters. We have negative 3 times 4. That gives us negative 12 down here. And then a times a squared gives us a to the third. Fantastic. Easy peasy lemon squeezy, right? Noteworthy here in this conversation. Hello, Jenna. I muted you while I'm doing the lecture. As I've talked about before, if you have questions, feel free to ask them now or wait till I'm done. Stop recording, then you can ask them because I'm recording this for YouTube. As we discussed before, we do have these operators involved in the equations, and it's important to not forget about those in the same way it's important not to forget about this negative number here. In this example, the publishers of the slideshow left the operators sitting in place like this. And then after they finished all of their math, they then adjust the operators as necessary, right? We already talked about how this got here. Here we have 3 times 5 is negative 15. Then a times a is a squared. And they had a subtraction in front of that, which then becomes a positive, right? This goes very deeply into the importance of writing everything out, being explicit about your work. Don't assume something because you're going to forget your assumption, right? Beyond all that, this is stuff we've talked about previously. I can do my example here. Again, if you're watching on YouTube, pause the video now, try to solve this, and then stop playing again afterwards. If you're watching this live, write this down, start going at it. My tempo will be a bit faster, obviously live, but we can make sure to figure it out. What is going on here? This is a binomial, a 2-part polynomial multiplied by a monomial, a 1-part polynomial. And this follows the same process we've been talking about. Distribute, multiply through, right? when I distribute this, I'm going to choose, in this example, to leave that, to keep that plus exactly where it is. Then if I want, I can maybe build around it, right? Likewise, I'm also going to do everything in parentheses so I make sure to keep all my information intact. This 5x is one term, so I'm going to keep that term inside the parenthesis. And that distributed minus 2x gets thrown up here. Likewise, the minus 2x gets thrown in the back, distributed to that 4. This positive sign here is connected to the 4, but I chose to leave it outside, and I think that's fine. It's another way of doing it. And then we have like terms to be multiplied by here. We've got everything organized accordingly. So negative 2x times 5x, multiply the numbers, multiply letters, stick them together. Negative 2 times 5 is negative 10. Here, let me just be very explicit about this. 2 times 5 is negative 10. And then x times x is x squared. Negative 10, x squared. Sweet. Plus, do the other part here, negative 2 times 4 times x, right? I'm clumping by like terms. Writing out explicitly what's going on here. Then my last thing is to rewrite this in descending order of the variable. So x squared is my biggest variable, so start that first. And then solve these plus minuses that are being thrown on over. Adding a negative 8x is the same thing as subtracting 8x. Huzzah! We have came to our solution. Hi, Amy. Quick spiel for you at begin everyone else. I am recording this for YouTube, so if you've got questions, you of course can ask me, or you can wait until I'm done, and then your questions won't be thrown on the YouTube video. It's up to you.
Okay, thank you.
No problem. Cool. Simple solution, right? This is, I keep beating this dead horse for a reason. Write everything out. If you feel like I don't need to write this out and you get it wrong, well, I know what you did, right? You didn't follow through with everything that needed to be done. You thought you could skip ahead and you lost something there, right? In this example here, they did not, as I showed previously, clump the like terms. They skipped the step of writing all that stuff out, right? That's fine. If you are smooth enough with this operation, let me make sure that looks correct there. If you are smooth enough with this operation to not have to rewrite out all the numbers together, all the like letters together, cool, fantastic, good for you. If you're not at that section, then this question is a 3-part question instead of a 2-part question. Right? I keep nailing this. I keep beating this dead horse. I'm not going to change analogies here for a reason. How to multiply 2 polynomials. Oh boy, right? When you multiply 2 polynomials, you do the same thing but more that we discussed with the monomials, namely distribute. You want to distribute everything out. You can distribute however you want technically, but the most common way that we go about distributing polynomials when we multiply them together is to distribute the smaller size polynomial into the bigger size polynomial. What do I mean by that? Here we have an example of y squared minus 4y minus 6, a trinomial, 3 terms, being multiplied by the in parentheses y plus 2, a binomial, a trinomial with 3 terms, and a binomial with 2 terms. The 2-term binomial is going to distribute itself into the 3-term trinomial. The 2-term binomial is going to distribute itself in a 3-term trinomial, meaning this y is going to distribute to each term, and this 2 is going to distribute to each term. And we're going to separate those distributions with whatever operator is in the smaller term here. It's long, it's drawn out, but it's the same math, right? It's the exact same math. And that's exactly what they did on this side here. You can see the y is distributed. You can see, let me get the spotlight here. You can see the y is distributed. The 2 is distributed. And then the plus sign, the operator for the smaller binomial, is set in place. And then you go about the process that we've discussed a lot before. Now, if you distribute the y and the 2, continue finishing up your distribution. Namely, this y gets sent throughout, landing us this guy here. The 2 is sent throughout, landing the other guy, and then combine them. Because since everything's at the same order of operations, everything's at the same part of PEMDAS in this middle stage here, everything's at the same operator level. You don't need the parentheses, so that's where minus 4y squared plus 2y becomes minus 2y. Right? The book likes to argue this vertical method. This one's always kind of bugged me, and you'll see why in a bit here. But the same rule applies. They stack the two binomials, and we have 6 plus 2, 4 plus y, and then you follow basic addition rules for vertical addition, wherein you take this term and you apply it everywhere. And then after that's done, let me change my color here. Let's go to purple. You take this term and you apply it everywhere. So this is step 2. This is step 1. And then those two are added together because these two are added together. I'm not a huge fan of this method. I think I don't see how the verticality benefits the conversation any. Again, notice they left the opening here because, again, the rules of addition, right? They left the opening here because that y is in the second spot. But if this is how you roll, if this is the way you like to do it, by all means, write this stuff vertically. Cool story. To me, there isn't a huge difference in these two ways, except that this way makes a bit more sense to me. And in the later on in this section, when we get to foiling, you're going to see why this method, I argue, is superior. But I'm not going to begrudge you. If you like to do vertical, you go right ahead. Right, in this example, all those empty spots annoy me. I'm not a huge fan of all those empty spots, which, as I said, is the reason why I don't do vertical. But if you look at that, you're like, you know what? That clicks with me. I like what I'm looking at here. Hey, do it. I'm not here to stop you. All right, so let's tackle this solution. Again, my suggestion to you is to, if you watch this on YouTube, pause the video here, try to solve this problem. If you're watching this live, hopefully you've already written this guy down and have started running through this process. I'll start here in just a couple of minutes. But before I start, reminder, your first thing, I have a trinomial multiplied by a binomial, a 3-term multiplied by a 2-term. I'm going to distribute the smaller one because that's just kind of easier. And then once I distribute it, I'm going to finish my distribution and end up at my solution. What do I mean by distribute? Well, I'm going to distribute this 2b to each of these 3. And I'm also going to distribute this 3 to each of those. I'm going to notice a plus sign between them. I'm going to carry that plus sign down with me. Put my plus sign here. And then I'm going to, again, keep everything in parentheses to make sure no information is lost. Let's say 2b times 2b cubed. Hopefully I don't run out of space here. And then I also have well, this is a good point to stop here. What do I do without that subtraction sign? do I carry it with the b in the parenthesis, or do I leave it outside? I'm going to make the argument here that since this plus sign was left out, this subtraction side should also be left out for the same purposes. It doesn't really matter. You can do it either way, but as long as you know what you're doing. 2b multiplied by b. That's supposed to be b's, not sixes. And then plus, oh my gosh, I didn't leave enough room, did I? Barely enough room. 2b multiplied by 1. I don't know why I'm squishing this. I can just erase it, redraw it. 2b multiplied by 1. There we go. Plus, distribute now the 3. 3 times 2b cubed minus 3 times b plus 3 times 1. 3. I've distributed both. I have my plus in the middle there. Now I can solve this, clump my like terms, find my solution, right? In the previous examples I rewrote these multiplication problems, clumping my numbers and my letters together in order to show what was happening. I'll continue doing that. Again, you don't need to write this step if you can do this step without needing to write it. I hope that makes sense. But once you get to the point where you don't need to write this step, you should write this step. Here, I'm going to separate out my 2's. 2 times 2 times b times b cubed. 2 times 2 is 4. B times b cubed is b to the 4th. Cool. Minus 2 times b times b. 2 is 2. B times b is b squared. That's 2b squared. My subtraction sign continues to fall down, right? Here I have 2 times 1 times b. Well, 2 times 1 is 2. B is b, and my plus sign falls right down. Likewise, this plus sign keeps falling down. And then I'm left over going over to the maroon, pink side. I don't know what color that is, top of my head. 3 times 2 times b cubed. Clump my like terms here, right? Giving me 6b cubed. My minus falls down, 3 times b. Well, I can do that one pretty easily. My plus falls down, 3 times 1. Again, I think I can do that in my head. Sweet. I have now taken that multiplication and wrote it as a big list of terms, all at the same level of order operations, all the same section of PEMDAS. Please excuse my dear Aunt Sally, the Aunt Sally pop addition subtraction. So if I rewrite this whole situation here in descending order based on the exponent of the variable, they're naturally going to clump in places that they share, allowing me to then finish out my math, right? The 4b starts. I see a to the 4th power up here, so I need to start. That's my biggest variable. That's the order of this new polynomial. So I'm going to stop and write all those out. 4b 4th. I finished doing them. I can cancel it. Pow, bang, smash. I can move down. Do I have any 3's? Hey, I do. I have a 6b to the 3rd. And it's positive because there's a plus in front of it. Plus 6b to the 3rd. Now that I've used it up, I'm going to make sure to explode it. Bow, bang, smash. Now I need to go on to seconds. I do have a 2b to the 2nd, and I notice that there is a subtraction sign in front of it, so I need to remember that subtraction sign. 2b to the 2nd. Excellent. Now I go to the first, or where there is no number, and I'll say I have 2 of them. I have a plus 2b and a minus 3b. Excellent. I've written those out. I can explode them. And then I have and on a plus 3. The only math at this point I need to do is I need to solve that minus that 2b and that 3b. That's again, those are b's, not 6's, except for the 6. That's a 6. To end up on my final solution. 4b the fourth plus 6b the third. Very obvious difference between 6 and b there. You're welcome. Minus 2b squared minus b, because there's 1b left over. It's a negative, so I don't write the 1 because you don't multiply things by 1 and show it, plus 3. And there we go. Is it a lot of work? Yes. I empathize with that, right? Is it a difficult sort of work? Well, not if you keep track of stuff, right? Not if you write everything down, not if you take notes of what you've used or what you haven't used, not if you're explicit about it. This stuff is more time consuming than it is difficult, I would argue. Because, right, we just follow our steps, we just take our time. Big important thing there, take our time. I know we all live in the real world. Sometimes time is in short supply. That's why I give you lots of time to finish your homework. All right, I'll clear this drawing and we'll move on. There we go. They did it vertically there. I don't see the benefit personally, but hey, they do. You do what you do. All right, so let's talk about multiplying two polynomials. Namely, what do we do if we have two binomials? This is super, super common. You can see this a lot. A situation where the first and the second part both are two-term equations. This here was a 3-term and a 2-term equation, and we just distributed the second term throughout, right? If they're both 2-term equations, we have a shortcut called FOIL written here, FOIL. First terms, outer terms, inner terms, last terms. This, like PEMDAS, you should write on top of your homework when you're doing this until you have it memorized. FOIL says when you have your binomials, look at the first term on each binomial, multiply those two together. That is the first term of your answer. The second term of your answer is going to be the outer parts of the binomials. This 2x is 5 on the outside parts of the equation. Multiply those two together, you have the second term of your answer. The inner terms, shown here, the 3 and the x, multiply those together, get the third term, and the last terms multiply together to get your last terms. First, outside, inside, last, FOIL. This essentially is the shortcutted version of distributing. If we wanted to distribute, we could. We would just get the same answer, but have to write more stuff down. That'd be the big difference. Notice here, when you distribute, you get this long chain, combine the like terms, and you get your answer. Saves a lot of the annoying parts of the classic distribute fiasco. Important to note here, FOIL only works with two binomials. If both equations that you're mathing around are two-term equations that are multiplied together, you can do this. As soon as one of those is not a two-term equation, you can't do this anymore. The simplicity of the method falls apart, and you get like really complicated equations that it's better just to do the hard work of distributing and trying to math it all apart. So let's do exactly that with this example here. Again, if you're watching YouTube, pause, try to solve this, and then come back. If you're doing it live, hopefully this speech has given you enough time to write the guy down so we can get going. I'm going to write on top of all of this FOIL, first, outside, inside, last. I'm going to follow the FOIL method to organize what I'm doing. The F in FOIL stands for first, so I'm going to take the first terms the first terms, yeah, I'll be explicit about this. The first terms being the 2a and the 3a, and I'm going to multiply them together. Makes that look better. There we go. Yeah, pretend that looks good. So I'm going to multiply 2a and 3a together. That, of course, lends me 6a squared. 2 times 3 is 6. A times a is a squared, right? Look at my outside terms, multiply those together. My outside terms have, again, that 2a. And, important part here, a negative 2. And this part, given the way the conversation happens, I'm going to drag that negative along with me. I am doing that because I want to make sure not to forget that negative exists. I don't have a way in FOIL of dropping down my operators like I did in the previous example that I showed you, right? The previous example where everything just kind of fell down in place as I was working it horizontally. The operators fell vertically. That's not an option with FOIL. So instead, I'm going to drag that negative, that subtraction sign in that second binomial, into a negative 2 for my outside terms. And then here we get minus 4a. Important note here, that negative was dragged along in the FOIL process, showing up as negative 4a. So I'm happy. Inside, my inside terms are a negative 1. Again, important to keep the negative. And a 3a. And doing this, I get negative 3a. My last terms are negative 1 and negative 2. Results in a positive 2. If you don't show a sign, you assume it's positive, right? Now that I have this, my overall answer without simplification is 6a squared minus 4a minus 3a plus 2. I combine my like terms in the center there. 6a squared minus 7a plus 2. Noteworthy also here, FOIL writes your binomial in descending order. If the original one's in descending order, my answer is in the descending order I need. My like terms are already clumped for me just by writing it. And I've essentially saved a lot of steps here. I didn't have to first distribute stuff because FOIL does the distribution for me. It's wonderful. It works for binomials only. Beyond 2 binomials, again, things get more complicated, but it's super effective. Write FOIL on top of your homework. Can't clump it like I just did here, right? Show the work. You're not going to get lost if you take the time to actually show the work. If you try to bulldoze through this, you're going to maybe run into an issue. Why bulldoze through it where you can just learn to do it correctly? And then get to the point where you don't need to write it down because you know what you're doing. Excellent. Let me erase this and we'll continue. Oh, hey, I did it correctly. Oh, go me. Yay. Woohoo. All right. Multiplying binomials have special products. These are your shortcut rules. You can always just do the math to get here, but if you want, we have special connections of stuff. For example, product of sum and differences are the same term. You have 2 binomials that have the same numbers in them. A and B are each same, right? A is 3, B is 2. And if one is positive, one is negative, the answer ends up looking something like this. It's a shortcut. It has its uses depending on what you do in life. It's a good thing to know. Couldn't hurt. The slides are on Moodle. This will be up on YouTube again if you don't finish writing this down by the time I fly past it. It's up to you. If I give you a question like this, where you notice that the A terms and the B terms are in fact the same things, and one is positive, one is addition, and one is subtraction, then you know the answer is going to be in the form of A squared minus B squared. And lo and behold, 2x times 2x is 4x squared. Ooh, that's gross looking. 2x times, we have little circles. Aha! 2x times 2x is 4x squared. 3 times 3 is 9. And this is subtraction between them. This is the form a squared minus b squared. You can just do the work, right? You can just do the work. Foil it out if you want. Or if you remember the shortcut, do the shortcut. It has its benefits. Not going to say it doesn't. If you have that same A and B thing going on, but they're both addition, then your answer ends up looking like this gobbled mess. Again, okay, cool. It's a shortcut. You can just do the work, but having the shortcut sitting there is, of course, useful. Again, we have our A and our B, and we close that A. There we go. And then this would be A squared to A B squared. Answers come out faster. You can still, of course, run through the effort of foiling it. You can distribute it if you really want to do a lot of work. This is just a shortcut, something that's useful. These are called, oh my gosh, I forgot what these are called. Oh, bad math teacher. Proofs? Yeah, I think these are proofs. Yeah, that makes sense. These are proofs. We'll go with that. So I give you examples such as this. The keen math student will realize, oh my gosh, that's in the form a minus b, a plus b. Oh, I'm so excited. Yay. And once you notice that, you know the answer is going to be in the form a squared minus b squared. Cool. And look at that, the answer is. I'll run through this foiling just to show you. Hopefully you can see why foil this would work the way it works, but I'm going to foil this anyways just for the fun of it. So if I'm going to foil it, I'm going to start with the first, which is going to be 4z times 4z. All right, 4z squared. Outside's going to give me 4z times positive 2w. Inside's going to land me at minus 2w times 4z. Again, we can already notice here the outside and the inside are opposites of each other, so they're going to cancel. And the last is going to be minus 2w times positive 2w, which is the last things are squared, but they're negative, right? Because there's one negative. Landed me at, in total, I'll put it right here, 4z squared plus, 16z squared. Thank you for correcting me, everyone. I can definitely tell you all noticed that error. I would just jump in the comments at that very moment to correct me. Thank you for that. 16z squared plus 8zw minus 8zw minus 4w squared. These two cancel each other out, landing us 16z squared minus 4w squared. Right? This and this are the same thing. I didn't have to foil it if I knew my proof. But foiling it gets you the exact same. It just takes a little bit longer. If you forget it, well, these things happen, right? It's up to you. Application problems. Yes, I can tell what you're thinking already. Yes, word problems. I've never been so happy. Oh my gosh. Yes, give me more. I completely understand. Everyone loves word problems. I just hope that other people in your house didn't hear your joy at seeing this, right? Let's try to keep it calm and professional. I give you a rectangle. I give you a yellow rectangle. I say the length of that yellow rectangle is x plus 7 meters. And the width of said yellow rectangle is x minus 4 meters. I can then stop and ask you, hey, find the area of the rectangle in terms of the variable x. Meaning, if I have this equation for a rectangle, I choose x to be basically any number, what is its area? Can you give me an equation for the area without having me first solving the length and the width? Well, I know from my vast experience with math equations that the area of something is given by its length multiplied by its width, right? So if the length is x plus 7 and the width is x minus 4, the total area is going to be equal to x plus 7 times x minus 4. Cool. Those are both binomials. They're multiplied together. I can FOIL this. I can FOIL this problem. Let's do it. On the next slide. Oop, oh, spotlight. Come here. There we go. Right. I take x plus 7, x minus 4, and I go FOIL. If you get good enough at FOIL where you write it out this way doesn't benefit you, don't write out FOIL. Until you get to the point where you're able to FOIL stuff without having to be explicit and write down FOIL and fill in those spots, please write down FOIL and fill in those spots. It's only going to help you learn, right? My firsts are going to be my x and my x times x. My outside is going to be x and minus 4. Those are the outside terms of these two binomials. My inside terms are 7 and x. And my last terms are 7 and minus 4. Excellent. Now let's stack it all together. My first terms become x squared. My outside terms become minus 4x. My inside terms become plus 7x. My last term becomes minus 28. Combine like terms, x squared plus 3x minus 28. Whatever I put in for x, the area of the rectangle will be resultant from this equation. Foiling. So easy, right? It's so useful and so easy, and we're so happy to be doing this. Integer exponents and scientific notation, the next section. Now we have an understanding of how to deal with polynomials of varying sizes and the various ways they can come together. Let's expand on these exact conversations. First thing to discuss here is how to deal with division and exponents on various factors. Remember previously we discussed if you have multiplication of different exponents on the same base, such as x squared multiplied by x to the third, you can rewrite that as that's supposed to be a 3, the exponents added together. X squared times x to the third is x to the fifth, because 2 plus 3 equals 5. So the multiplication steps down to addition when you deal with the exponents. Likewise, division steps down to subtraction. If I was to divide x to the third by x squared, that's the equivalent of saying x to the 3 minus 2, or just x to the first. Exact same thing. Important note here, I think we're going to hit this up soon, but important note here is when you are subtracting stuff this way, you can run into negatives, right? What if this was x squared over x to the fifth? What would happen in this scenario? Well, that would be x times 2 minus 5 would be x to the negative third, right? What is that? Oh my gosh. I'm tailboat writing with a mouse. What does x to the negative third mean? Well, let's look at the examples given here. Notice this x squared at the bottom means there's two x's on the bottom, right? A negative exponent simply means those variables are in the denominator. That's all it means. Again, I think they're going to cover this anyways, but I wanted to make sure to touch on that. A to the 7th, so I have a to the 3rd, becomes a to the 4th. Not too bad, right? A couple other shorthand conversations to have. Anything divided by itself is 1. Right, we already knew that. Anything divided by itself is 1. I guess I don't need to keep repeating myself. But the weird part about that is that means x to the 0 or anything to the 0 power is equivalent to 1. And that seems like kind of a weird thing to think about, right? How do you have a 0 of something means you have a 1? But it comes from that idea that the top 1 means the top and bottom are the same, right? 5 divided by 5 is equal to 1. The 5 and the 5 are the same number. So when I take that 5 divided by itself, I get 1. I have 5 pieces of cake. I have 5 friends come over for my birthday. That means I have 1 good birthday party, right? What is that? That is the same thing on the top and the bottom. And we also know that if you divide exponents, you subtract them. So 4 minus 4 becomes 0, right? And that's also equal to 1. Therefore, x to the 0 equals 1. Don't worry about getting too stuck up in it. Just try to, I would argue, try to remember this basic concept. Anything over itself is 1. Keep that idea in your head, and you should be fine. Yeah, anything to the 0 is 1. 0 to the 0 doesn't make sense, so we don't worry about it. But yeah, hopefully this sticks. We can ask me questions when this is over if you want. I'm probably going to be recording for another 20 minutes or so. So you can always ask me questions in the comments, ask questions when I'm done recording if you want. It's a weird I grant it's a weird concept, but I hope it's sort of kind of making sense when you look at these examples. This is what we already touched upon. The idea that a negative exponent is just an exponent in the denominator. It's not any scarier than that. You can, in fact, rewrite them either way, which is kind of fun. This is the same as that, and this is the same as that. Both are equally viable ways to write the answer to this particular question. Classically, you're probably... Actually, I don't really know if there is a preferred one or the other. I really don't know. It's all context based on who's asking the question. If you end up writing negative exponents in your homework, or if you end up writing fractions with exponents in your homework, I'm going to accept both. Whatever, I guess, floats your boat better until you get to the point where someone's paying you to write this information. Then they're going to know what they want. Yeah. This is more the same stuff. I guess I don't need to... It would benefit if we were in class that I could, stare you guys all down and make sure you all understand it. But yeah, if you guys got questions, you can always type them in the chat if you don't want to speak on the YouTube channel, or we can wait till we're done and you can make sure to ask the questions. It's up to you. But I'm going to assume everyone's perfectly understanding everything that's going on. I'll just continue. This one's kind of cool. Working these weird exponent ideas into actually meaning something. Here we have 2 raised to the negative 4th power. What? Right? What? I can figure out 2 to the 4th power. I know what that means. That's 2 multiplied by itself 4 times, right? 2 times 2 is 4, times 2 is 8, times 2 is 16. But to the negative 4th power, that's a bit of a mind screw, right? What is that trying to tell me? Well, I need to remember that the negative in this scenario is not like a negative in addition subtraction, right? We're not doing negative 4 as itself being a negative 4. We're treating that negative of the exponent as a signifier that everything that's going on is in the denominator. That negative doesn't mean negative 4 as much as, again, it means denominator is the place all this stuff is going down. Or this conversation, this guy leads in here, which then leads us to our answer. 2 to the negative 4th is the same thing as saying 1/16. I don't think anyone's ever going to ask you for 2 to the negative 4th of something. They're probably just asking you for 1/16 of it. But if you want to impress people at your next birthday, invite 16 people over and tell them they're all getting 2 to the negative 4th slices of birthday cake. And hopefully your friends will be like, wow, your math's so good. I'm so happy I came here to eat 2 to the negative 4th birthday cake. As you technically be right, I guess. Yeah. Just gonna continue going through this. I don't know how many times I can repeat these conversations. Negatives, positives, what have you. If you remember that simple math we talked about before, wherein multiplying exponents is add the little numbers, divide exponents is subtract the little numbers, this complicated math becomes much easier. So, how to evaluate 5 to the negative 2nd power divided by 5? Well, a couple ways to handle this is to first of all remember that the negative 2nd power, well, actually, I keep forgetting I have circles and stuff like that. I got squares even. Oh yeah, like I said, that's so professional. The negative 2nd power simply means whatever's going on is in the denominator. So the book's approach here is a good one, to use the concept of dividing exponents, realizing this bottom essentially has a little 1 next to it, and then write out 5 negative 2nd minus 1, because a division of exponents is a subtraction of those little teeny numbers to give me 5 to the negative 3rd, and then write that as a fraction to get me what I want. That is correct. Any way you want to look at this problem, you will resolve, if you do the math correctly, the same solution. You could, if you want to, rewrite that. Here, let's drag this guy down here. You could, if you wanted to, rewrite that negative 2nd in the bottom. By that I mean, you could write this as 1 over 5 to the 2nd times 5. Because that negative 2 is just a 2 in the bottom. Value 5 to the 3rd. That's the same thing. And just instead of doing the math, you just relocate it so it doesn't need the negative number. That what I just showed you might actually be useful in later examples when we're dealing with big, complicated divisions of conversations. It'll be up to you. This is something I think we covered before as well, but we've talked about multiplied exponents. We've talked about dividing exponents. What if you exponent an exponent, right? Exponenting an exponent, that's not a word, I'm going to stop saying that, follows the same basic idea, wherein you just kind of take it the step down. Where multiplication becomes addition and division becomes subtraction, raising to the power becomes multiplication. So I have these examples down here, where you essentially take this 2 and distribute it to the top and to the bottom. 4 times 2 is 8. 0 times 2 is 6, giving me x to the 8th, y to the 6th. I guess is the point in the conversation where I usually remind you all that this stuff is annoying, this stuff is difficult, and you really only gonna learn it well by doing it. I apologize. I don't have a shortcut for you, and if the shortcut existed, I'd prefer you to just know how to do it. So lots of different little rules. It may be of benefit to you to maybe write some of these rules down in a place you can easily go back to. Maybe at the top of your homework, just do write a couple of these quick little examples up there so you can remember how the heck this works. However you choose to do it's up to you. But these shortcut rules are going to be very beneficial to you in not having to draw out stuff as much as necessary. Right? This top example here, a to the 4th divided by b to the 6th to the 3rd power. Expanding that out gives you, using the definition of an exponent, 6. Oh my gosh, I need to erase that. It's horrible looking. Expanding that out means 3 different copies of a to the 4th divided by b to the 6th, all multiplied to each other, right? And then we multiply straight across to give us 4 times 3 is 12, and 6 times 3 is 18. A to the 12th, b to the 18th, right? That's the long form version. The short form version, of course, would be, I'll show it down here. Oops, erase that real quick. Squared would be to just distribute the 2 throughout. 5 squared over 7 squared to give me 25 over 49. Same conversation. I think you will find it beneficial to not have to write out these big terms if you just remember to distribute the 3 throughout, like shown here. If you end up needing to draw out those big expanded equations, more power to you. I have no problem with that, obviously. Rule applies if the exponent's a negative. Same conversation keeps happening, right? This one's kind of fun because the negative exponent essentially flips the exponents. And that's something that hopefully you would recognize in process. Hopefully this section here, the distributes -2, is well and good enough. But this part on the bottom here may be kind of what's going on here. My suggestion to you is when you get your answer, if you don't know just to flip them, you can slow it down and work each one individually. By that, I mean a to the -6th, well, that's an a in the bottom, right? So that's an a to the 6th at the bottom. But if a negative makes the top go to the bottom, a negative in the bottom would therefore go to the top, right? Because you're just switching position. So b to the -4th in the denominator is a b to the 4th in the numerator. Right? You don't have to do it in one step like the slide shows at the top there. You can do them in individual steps like shown here. And of course, as I've said a few times, God's honest truth, you're probably just going to want to have to do this a few times until you get the flow and the idea of what's being expressed here. More examples of the same concept. Cool. And there's your big long list. If you want, all of these are the generic versions of the equations and proofs that we've been showing throughout this lecture. I can suggest to you, if this is stuff that isn't quite clicking with you, feel free to write all these down. on the top of your homework and just section back to them. Feel free to bookmark the particular page in your book that has this. I don't know what it is off the top of my head, and reference back to it. This stuff really just comes from doing it. You're not going to shortcut your way to solving these problems. If you do shortcut your way, I hope you're not my nurse. I don't want my nurse taking shortcuts, right? Cool. So let's do some quick math with these complicated parts to them. We notice here, we've got these big, long stacks of multiplications. Since everything in this conversation is multiplication, we kind of don't need the parentheses, right? So I can rewrite this clumping all of my terms. I can clump my 3 with my -2. Actually, let's do this completely without parentheses. I can clump my 3 with my -2. And then I can put all my A's in a row. I got one A on the left there. I've got A to the -3rd on the right there. And I've got a B to the -4th. I've got a B to the 7th. So I can solve all my numbers. I can solve all my A's. I can solve all my B's. The end result being, hopefully, an answer that makes sense. 3 times -2, that is -6. A times A to the -3rd. What's going on there? Let me make this negative a bit more negative-y. There we go. Well, when I have multiplication of exponents with the same base, meaning the big number in the bottom, the big symbol, letter, number in the bottom is the same, and the numbers in the top are multiplied, I add them. So this turns into, as shown exactly down below, 1 plus -3. 1 plus -3 is -2. So A to the -2nd. Oh, that's a terrible 2. -2nd. Excellent. Now I can move on to my B's. B to the 7th plus B to the -4th, so 7 minus 4, gives me B to the 3rd. Excellent. The last thing I need to worry about is I don't want, if you can try to avoid writing negative exponents when possible, I think that's a good move in general. Again, I'm not going to mark you down if you don't, but it's kind of common not to see them, and it's kind of common to see them, right? That's the annoying part. Both of those answers mean the same thing, and both of those are technically correct. I don't know where you're going to work post-graduation. I don't know which is going to be preferable to your employer. It's good to know both, to be honest. It's the most important thing is to realize that they are the same equation. That's the most important thing. All right. So I think we'll end the recording for today on this particular example. I'll run through it in just a bit, but of course I'm giving you time, if you watch this via YouTube, to pause the video and do it yourself. If you're doing this in the live recording, I'm giving you the time to write this equation down and start working on it before I get going on it. So I have the quantity minus 2x multiplied by the quantity 3 times x to the -2nd. That second quantity is raised to the -3rd power. Oh boy, a lot going on here, right? So we need to solve this to the best of our abilities. We enter now an issue that we haven't talked about in quite a while, which is order of operations. Because what do we have here? We have multiplication. We have multiplication right here between those two, but we also have that -3 as an exponent. That -3, PEMDAS says exponents happen before multiplication. We should solve that exponent before we do the multiplication of the two parts. Or by that I mean I shouldn't multiply the 2x into stuff first. Instead, I'm going to send the -3 inside here. When I do that, what happens? Well, the in total 3x negative second gets multiplied 3 times by itself in the denominator, right? The long form version of this is a part here we're learning some of these rules can be of benefit, not shortcuts, rules can be of benefit. This guy here translates into 1/3 x negative second times 1/3 x negative second times 1/3 x negative second, which in itself means x squared over 3 times x squared over 3 times x squared over 3. That's less tough to have to memorize, right? That's a pain. So instead of doing all that work, just give it a view. We can remember how the distribution feature works, right? We can remember to send that -3 to everything inside there. Or, if you will, 3 to -3rd, and then x is -2nd raised to -3rd power. When I have an exponent and I multiply and I raise it to another exponent, that's the same thing what? As multiplication, right? 3 to the -3rd, and then x to the -2nd times -3rd. -2 times -3 is +6. So 3 to the -3rd, x to the 6th. All right, sweet. What is 3 to the -3rd? Well, that is the same thing as the negative says, put the number from the numerator to the denominator or vice versa. So that means, keep doing the equal signs there, 1/3 to the 3rd times x to the 6th. 3 to the 3rd, 3 times 3 is 9, which is what, 18? Well, actually, slow down. Let's slow down a bit. That is my second half of the equation. The first half of the equation becomes, let's just finish this guy out. 6, 3 times, 3 times 3 is 9, times 3 is 27. The first half of the equation essentially has been untouched, which is -2x. Now we're in a scenario here where just regular multiplication, right? -2x times multiply straight across. -2 x to the 7th over 27. Ooh, that's gross looking. Right? A lot of stuff happens. A lot of stuff goes on in these equations. And let me back this up a bit. There we go. Get out of the way. As I've said countless times, right? These things can be daunting if you try to skip steps or you try to run fast. If you stop if you look at what you're writing, write it down, solve each, treat this not as one big problem, but as 5 little problems, you will find the solution to be much less confusing, I hope. Yeah, that's kind of the whole point of this, right? Is to teach you these basics. That way, when you get to more advanced stuff, you can fall back on your basics to get you there. I guess, yeah, that'll be good for, yes, we can start scientific notation next class, slide 73. I'll sure forget that. And I guess for this particular conversation, I'll end recording now. Thank you for watching, everyone on YouTube. Thank you for participating, everyone in class. Once I stop recording, if you want, you can ask me questions or head out. Take care.